So good. So good morning or good afternoon, everybody, and welcome to the third and last day of this IBS ICTP workshop on Alps. Today, it's my pleasure to introduce the first speaker, Takeshi Kobayashi, who's going to talk about, I also have to reduce the screen or I cannot read the title, Axions, dark matter, and primordial density perturbations. So Takeshi, the stage is yours, please.
Okay, thanks, Lorenzo. And I should also start by thanking the organizers for organizing this great event and also for having me here. Well, I'm sure that the past 2 days were also great, but I have to confess that I just came back from an international trip last week. And so I'm still doing a self-quarantine at home with my son, which has prevented me from attending the talks in the past days, unfortunately. So I may end up talking about something that was already covered in the previous talk. So if that happens, please let me know so that I can skip that part of my talk. Oh, and also, if there's any questions or comments or anything during my talk, feel free to interrupt me at any point and ask questions. Okay, so I was asked to talk about axions and cosmology, so I decided to talk about, introduce some of my works that I've been doing in the past few years, which is basically about the evolution of axions in the early universe. So here is the outline of my talk. So I will start with a brief review of axion cosmology. For this audience, I'm pretty sure that this is not really necessary, and there's a lot of experts out there. But just to make sure that everyone is on the same page, I will start with a brief review. And then I'll talk about 3 topics. In the first two, I'll basically point out that what is usually considered to be the standard lore of axion cosmology is not that firm, and there's a lot of wiggle room for that. So I will try to show that through these 2 examples. And here, my main focus will be on axion dark matter. And then in the last part, I will slightly switch gear and I will point out that axions are not only good for dark matter, but they're also good for explaining the origin of the density perturbation of our universe. And for this first part, this will be based on a series of papers that I wrote with Lorenzo Valli, who's moderating the session. So if you have any questions, you can also ask him. The second part, this was a work with Rajiv Jain at Bangalore. Okay, so let me start with a brief review of axion cosmology. So in my talk, at least in the next 1 hour, when I say axion, I will refer to a generic pseudonumber Goldstone boson of some spontaneously broken global U1 symmetry. So this is a very broad definition, which includes, of course, the QCD axion for solving the strong CP problem, but it also includes all sorts of axion-like particles, including those arising from string compactifications. So with this broad definition, the axion is basically a phase direction of some complex field. But the wine bottle is not exactly flat because it's a Navier-Goldstone boson of a global U1, which can be broken by various effects. If it's a QCD axion, it will be broken by the QCD effects, but it can also be broken by quantum gravity or whatsoever. So the point is that the axion, at the wine bottle minimum, it feels some potential. But another important thing is that this potential is periodic because it's basically a phase direction. So there's basically 2 important scales that are important when discussing axions. The first is the periodicity of this periodic potential, which is often related to the symmetry breaking scale and also referred to as a decay constant, F, and the mass of the axion, which also kind of describes the height of the potential. Of course, for the QCD axion, the mass and the decay constant are not independent. Their product is basically set by the QCD scale. But for a generic axion, these 2 can be completely independent from each other. Okay, and when it comes to the cosmological evolution of axions in the early universe, one important concept, a concept that will pretty much underline my talk in the next 1 hour, is the idea of vacuum misalignment. So this happens if the spontaneous symmetry breaking happens before inflation, namely if the symmetry breaking scale is larger than the inflationary Hubble parameter. In this case, inflation basically homogenizes the axion field. So the axion field will take one value in the entire observable universe. And also, the field will be stuck at some point along its energy potential, basically due to the strong Hubble friction in the early universe. But as the universe cools down, eventually the Hubble friction becomes weaker. So the axion, oh, before that, yes. And I said that the axion is initially frozen at some initial value. And this initial value is pretty much random. And so typically it is displaced from its minimum by some order unity angle. And the next thing is that at some point the universe cools down and then the Hubble friction becomes weak. So the axion starts to oscillate about its potential minimum. And at this point, this oscillating axion field is it basically corresponds to a large number of axion-like particles. So at this point, you can say that axion dark matter has been produced. So this is a vacuum misalignment mechanism. So it's quite a simple mechanism. And you can also say that this is pretty much inevitable. Even if you don't want your axion to be dark matter, if you have axions in your theory, this vacuum misalignment pretty much happens inevitably as long as the symmetry breaking happens before inflation. So you will end up with some amount of axion dark matter. And here I'm showing you the relic abundance of axions produced from this vacuum misalignment. Here I'm showing you the case for axion-like particles whose mass is independent of time. So this is not the case for example, for QCD axions or its variant whose mass is temperature dependent. Here I'm showing you the simplest case where the axion's mass is time independent. So in that case, this is the expression for the relic abundance, and you can see that this will make up the entire dark matter if the initial misalignment angle is a typical order unity, and the decay constant is set to 17 GeV, and the mass takes an ultralight value of 10 to the minus 22 electron volt. And these kind of ultralight axion dark matter, this also has gained a lot of attention over the years because it has the potential to solve the so-called small-scale crisis of cold dark matter. I think there were also some talks on ultralight axions in the past days, in yesterday or the day before. But the point is that so cold dark matter, the traditional pressureless cold dark matter, seems to have some sort of tension with astrophysical observations on small scales like at galactic scales. But the point is that if your dark matter is actually an ultralight axion with this kind of mass, then its de Broglie wavelengths would be huge, like on galactic scales. And below that scale, the axion it doesn't really behave like particles, it will behave more like waves. So the structure formation changes. And as a consequence, this works in the direction of solving the small scale tensions. And so from this point of view, these ultralight axions gained a lot of attention, but eventually it turned out that while they can potentially solve these issues, they're also in tension with other astrophysical observations like those from the Lyman alpha forest and also for galaxy rotation curves. So the moment it seems like they're not that good for solving small scale crisis of cold dark matter. However, still, if you just have a larger mass and a smaller decay constant, then you can make up the entire dark matter. You won't be able to solve the small scale issues, but still you can make up the entire dark matter. So axion-like particles remain to be a good candidate of dark matter. Another thing to mention is that there's also constraints from axion isocurvature perturbations. The point is that, as I said, I said that inflation homogenizes the axion field, but at the same time, during inflation, axions obtain tiny density fluctuations, basically starting as quantum fluctuations sourced during inflation. And as a consequence, the axion density will be slightly different among different patches of the universe. And these are called isocurvature perturbations and are strongly constrained from CMB observations. So you also have constraints from that. So when you take these into account, you can get this kind of a constraint for axion-like particles for the mass and the decay constant. So this upper right quarter is ruled out because your axion will over-dominate the universe. This part is in tension with Lyman alpha forest. So you have to be in this red region. the constraints from the ISO curvature perturbation depends on the inflation scale. So we don't really have a definite constraint from there. But if upcoming CMB observations detect some sort of primordial gravitational waves, then you can use that to pin down the inflation scale. And then you will get some definite constraint from ISO curvature perturbations, such as these, depending on the value of the density to scalar ratio. But the main message here is that here, I didn't mention anything about axion matter couplings. All I mentioned is basically constraints from gravitational physics or cosmological constraints. And you can already see that just from these gravitational or cosmological considerations, you can put pretty strong constraints on axions. So it's quite powerful. Okay, so what I just mentioned is basically the vacuum misalignment scenario, which works, as I said, if the symmetry break-in scale is higher than the inflation scale and also the reheating temperature. There's an alternative possibility, which happens if the inflation scale is higher than the symmetry breaking scale. In this case, what happens is that the spontaneous symmetry breaking happens after inflation. So you will end up producing topological defects, namely axion strings and axion walls, domain walls. And so, if the domain walls remain, it's kind of a disaster for cosmology, but in a subclass of theories, you can make these domain walls disappear. And then you can have a viable cosmology, and you can also have Axion dark matter production basically from the emission from these topological defects. So this is also a viable scenario. However, the actual value of, for example, the symmetry breaking scale in order to get the right abundance of Axion dark matter, say, is kind of difficult to know. Well, there's experts, I suppose, in the audience like Giovanni Viradoro who can tell you a lot about these things. But my understanding is that this is when you try to actually numerically simulate this thing, it's very difficult, and we won't be able to get a definite answer for the next quite a long time. But anyhow, this remains a valid possibility. So this, yes, and I should also, so these two are basically the two main possibilities for the axion evolution in the early universe. I should also mention that this vacuum misalignment does not work if your inflation scale is very low. So if your inflation Hubble is lower than the axion mass, then what happens is that the axion basically, the Hubble friction is so weak such that the axion field gets stuck at its potential minimum already during inflation. So you wouldn't have any vacuum misalignment. So this is pretty much a deserted area where you won't be able to produce any axion dark matter. Okay, so this is pretty much the lightning review of axion cosmology. And this is pretty much the standard lore. But one of the goals of my talk today is to ask the question of how robust are these arguments? Is the standard lore something that is completely established, or are there a lot of wiggle rooms? And of course, there are wiggle rooms. And as one such example, I will start by discussing a new production mechanism for axion dark matter, which can work in this very low inflation scale regime, which has considered to be the deserted area. But you can actually have axion dark matter here. So I will start by introducing that. So this will be the topic of my first part. Okay, well, if there's no questions, let me move on. Okay, so I'm going to start by discussing this new dark matter, axion dark matter production mechanism that works with a very low inflation scale. And for this mechanism, we decided to call it the inflaxion, and I hope the reason will become clear soon. So the main ingredients are the following. The first is the axion field, which I describe by sigma, of course, because we're talking about axions. And the second ingredient is the inflaton field. Okay. If you believe in inflation, it is probably driven by some sort of scalar or pseudoscalar. So I will just call that a phi. The point is that if you have an axion and if you also have an inflaton in your theory, why not have a kinetic mixing between them? The point is that this is a dimension 4 operator, which respects the shift symmetry of the axion. So from the effective field theory point of view, there's a priori no reason to forbid such a coupling. And the point here is that once you allow for such a coupling, this can strongly modify the axion dynamics, and in particular, it can lead to axion dark matter production in the early universe. So let me explain how this works. So this mechanism can also work with high inflation scales, but here I will focus on low inflation scales, in particular where the Hubble parameter during inflation is lower than the axion mass, because this is basically the regime where usually you won't have any axion dark matter production. So this is the way it works. So during inflation, the inflaton field it basically just slowly rolls along its inflationary plateau. Okay. On the other hand, if it were not for this kinetic mixing, the axion would just get stuck at its potential minimum, basically because the Hubble friction is so weak, and so the axion just gets stuck at its potential minimum. On the other hand, if you have this kinetic mixing after an integration by parts, this is basically axion coupled to box phi. So if you have a slowly rolling infiltrate, this basically sources an effective linear potential for the axion. So it basically kicks the axion out of its minimum. So in this way, basically due to the dynamics of the infiltrate, the axion obtains a misalignment from the vacuum. And then after inflation, the two fields starts to oscillate. And then you have this oscillating axion field, which is basically a large number of axion dark matter particles. So this is the main mechanism of inflaxion. It's very simple. When you actually look at the actual field dynamics, it looks like this. So as the inflaton field starts to roll quickly towards its potential minimum towards the end of inflation, the axion gets kicked out of its minimum and out of its vacuum. And then after that, both fields oscillate. And you can also see that this is a kind of a double oscillation. I mean, it's oscillating with two frequencies. And that's because you have the kinetic mixing. The point is that the fields, infiltrate and the axion, are not diagonal. So that's why you have this double oscillation. So then the natural question you probably have is that what is actually happening if you go to the diagonal basis? Of course, you can always simultaneously diagonalize both the kinetic terms and the potential terms up to quadratic order. So if you move to the diagonal basis, what happens is that during inflation, you have one light degree of freedom, which is basically the effective single field infiltrate whose field fluctuation sources the density perturbation of our universe. On the other hand, you also have this very heavy field, which is just stuck and stabilized at its potential minimum. Okay. So it's basically just one degree, it's a one field cosmology. And so you may be wondering then, like, where does the dark matter degree of freedom show up from at the end? The point is that the inflaton mass, the effective mass, is different between during inflation on this inflationary plateau and after inflation at this true vacuum. And due to this time dependence of the inflaton mass, the diagonal basis rotates, becomes different during inflation and after inflation. So the old, what used to be the two diagonal fields during inflation, they split into new two diagonal fields after inflation. And then among the new two diagonal fields, the heavier one basically is less stable, and so at some point it decays and it reheats the universe. So it basically plays a role of a reheaton. And then the lighter one, if it's light enough, it can survive until today and serve as dark matter. So this is basically what's happening. Okay, and I think at this point you notice that all the important players in cosmology are basically described by different linear combinations of the inflaton and the axion. The field that reheats the universe, the field that sources density perturbation, and the one that sources the one that plays the role of dark matter. They're basically just different combinations of the inflaton and axion. And so we decided to call out all of these the inflaxions. So that's why we decided to come up with this name. And so it's basically an inflaxion cosmology. Okay. And here I'm showing you examples of the parameter window where this inflaxion mechanism operates. Unfortunately, I don't have time to talk about the details, but the main message here is that this inflaxion mechanism works both with axion-like particles with a constant mass and also QCD axions. and also QCD Axion-like axions coupled to some QCD-like strong group, QCD-like gauge group in the dark. And the point is that this inflaxion mechanism, it opens up new, because it's a new dark matter production mechanism, it opens up new axion windows. And in particular, it explores very low inflation scales and also large decay constants. The point is that typically, if you have a large decay constant, your axion in standard scenarios like the standard vacuum misalignment, if you have a large decay constant, your axion tends to over-dominate the universe. But the point is that for the inflaxion, the misalignment is basically sourced by the dynamics of the inflaton. And so the misalignment tends to be small. So in some sense, you have some sort of a dynamical fine-tuning of the misalignment angle, which is kind of tuned to be small naturally. And so that's why you can have a viable window even with a high decay constant. Okay, and then what are the smoking guns? Well, the most important thing is that there's inevitably a link between the reheating temperature and the axion matter couplings. And this is basically because of the kinetic mixing between the inflaton and the axion. Because of this kinetic mixing, the matter couplings of the axion and the inflaton, they share their mutual, they share their matter couplings. And so the point is that even if your axion has a rather large decay constant, it can have a pretty strong couplings to matter through the inflaton. And so some typical fun consequences is that the axion dark matter can have a rather short lifetime, even if your decay constant is large. And if this lifetime is so short, such that if it's comparable to, for example, the age of the universe, then you can have fun astrophysical consequences. Another point is that even if your decay constant is large, the axion can rather non-negligibly interact with normal matter. And actually, some parts of the inflaxion window can be probed by upcoming experiments like Abracadabra. I should also mention that when you apply this inflaxion mechanism with the QCD axion, then there's some further restrictions, and the reheating is kind of pretty much restricted to go into neutrinos. And so for this QCD inflaxion, you can also have fun experimental consequences in neutrino physics. And the last part is that unlike in standard scenarios like vacuum misalignment, for the inflaxion mechanism, you don't have any dark matter isocurvature perturbation. And the reason is because, as I said, it's during inflation, it's basically a single field model. And so that's why you don't have any dark matter isocurvature perturbation. So you pretty much escape those traditional cosmological constraints. Okay, so that was the story about the inflaxion. If there's any questions, you can ask at this point. Well, you can always ask any point. But if not, I will move on to the second part of my talk. Okay.
I do have a question.
Sure.
If you go back to the 3 plots you showed, I'm wondering, how would this picture qualitatively change if the coupling was smaller? It's my understanding that all 3 are for a coupling alpha 1/3. So if you made it an order of magnitude smaller, what would change in these plots?
Okay. Well, as you can imagine, the coupling, it's more preferable if the coupling is large. If the coupling becomes smaller, the window shrinks, but it also moves in some direction. Which direction it moves depends on the exact scenario. And I cannot tell you because I don't remember. But the point is that it both moves and also the window itself becomes small.
All right, thank you.
Yeah. So if this coupling is like super small, then it becomes more and more kind of the window becomes tinier. Okay.
Right, thanks.
Okay, so thanks for asking. Good. Okay, so if not, let me move on to the second part. Okay. Good. So, but before doing that, let me just quickly recap what was the inflaxion. So the point of the inflaxion was that when you have a shift symmetric coupling between the inflaton and the axion, and then this basically modifies the axion dynamics, and it allows dark matter production even with very low inflation scales. So this was the idea of the inflaxion. So I think you start to wonder, okay, maybe you can also have something similar with other kind of axion couplings. For example, the typical axion couplings to the gauge bosons, the axion FF tilde type. And the point is that this FF tilde, this is a parity violating combination, and this is basically proportional to the dot product of the electric and the magnetic field composed of this gauge boson. And so if your electromagnetic field doesn't have a specific parity, then this combination disappears. But if you have a helical, electromagnetic field with a certain helicity, then this part will be non-vanishing. And so this combination will also affect the axion dynamics. And on the other hand, nowadays, there's quite a lot of motivations to think about gauge fields being excited in the early universe. For example, one typical reason is to think about the origin of the magnetic fields in our universe. One possibility is that the magnetic fields in the universe have a primordial origin. In that case, the magnetic fields have to be excited in the early universe. Another reason why people think about gauge fields excitations is because they try to excite gauge fields, particularly in a dark sector, in order to use that to source primordial gravitational waves. There are also people who think about vector dark matter, and that's also a kind of a gauge field excitation in the early universe. I think Lorenzo is an expert on this. Okay. On the other hand, there's a lot of gauge field excitation mechanisms that also violate parity. And so the point is that for any of these reasons, if you end up producing some amount of a background of helical electromagnetic fields in the universe, in the early universe, this can have a strong impact on the axion evolution. So let me demonstrate how this works. Okay. So in order to make the story simple, I'm going to consider a simple case. I'm going to consider an axion coupled to hidden photon, so a dark U1. And I'm also going to assume that for some reasons, these dark photons were excited in the early universe to form a homogeneous background of an E dot B. Okay. And then what happens is that this E dot B basically gives an effective linear potential to the axion through this axion FF tilde coupling. And so it basically serves as something like wind that is blowing in one direction to the axion. And so this basically sources a field velocity to the axion. And if this field velocity is sufficiently large, then the axion will go over the hill and it will continue to move in one direction. So if you look at the Pechay-Kun field, it's basically like the field is moving in one direction along the phase direction. And if this happens all the way until the time when the axion is supposed to begin its oscillation, then this will delay the onset of the axion oscillation. And if the axion oscillation is delayed, at the end, you will have an enhancement of the axion relic. And the point is that if you end up producing an E dot B background in the early universe, this will at the end enhance the relic abundance of axions that are coupled to the gauge bosons that make up these E dot B. Okay. So in order to see the impact of this, I'm going to consider the case for the QCD axion, which is assumed here to couple to dark photons. Okay. So for the QCD axion, this is the relic abundance produced from a vacuum misalignment. Okay. And so you can see that if with misalignment angle of order unity, if your decay constant is around 10 to the 12 GeV, you can make up the entire dark matter abundance. On the other hand, if your F becomes larger, you go into the so-called anthropic regime, which is basically the regime where you have to somewhat make this misalignment very tiny. Okay. On the other hand, if you go to small decay constants, you have astrophysical bounds from stellar cooling, like supernovae, etc., which I think was covered yesterday. Okay, so this is a standard story. But now what happens when you have an E.B background in the universe? First, let me mention that since we're considering dark photons, there's also constraints on their abundance, basically from the effective relativistic degree of freedom, which basically are constrained from CMB and also BBN. So here, if I define the effective number of E.B in kind of this standard way, I mean, in a way that reminiscent of the way you compute the relative abundance, the number of relativistic degrees of freedom, then this is bounded from above to be something like 10% or something from CMB constraints. Okay, so now what happens? If you have an E.B background, basically, if you're on the left part of this orange line, then the E.B will modify the axion dynamics, and it will basically enhance the relative abundance. And so if you're on the left side of this orange line, the expression for the relative abundance is no longer this traditional one, but it turns into this one, which now depends on the amplitude of the product of the axion coupling and the effective relativistic degree of freedom of the E.B, which is shown as this y-axis. And importantly, if you're in this red region, your the E.B is strong enough that the final relative abundance becomes larger. It basically overdominates the universe. So you can see that when this product is as small as like 10 to the minus 12, then you're already completely closing the QCD axion window. Okay. So in the presence of E.B, you can produce the right amount of axion dark matter if you're on this black dashed line, but if you're above, you overproduce axion dark matter. So you basically completely close the axion window. And this happens already when this product is something like 10 to the minus 12. So it's a pretty strong effect. Okay. So, and some comments about.
Sorry, I have a question in the previous slide.
Sure.
So here, the exponent of f is changed from plus to minus. Is it typo or?
No, it actually changes.
It's.
Yeah, the point is that, okay, let me see. The way you can understand this is that it's more like, okay. Okay, I'll explain. So the point is that where does this threshold come from? The point is that if you have an E.B, as I said, the axion moves in one direction, okay? And when the induced kinetic energy of the axion is larger than the height of the axion potential, then the axion kind of goes over the hill and continues to move in one direction. And if this happens all the way until the time of the QCD scale, then it basically completely changes the axion dynamics. And so that's the threshold shown by this orange line. And now you're asking, why does it depend negatively, right, with this f? So let me see if I can explain this. Let me see if you have, let me see if you have a large, I think you can understand this. Yeah, yes, because if you have a smaller f, so this is the induced field velocity of the axion, and you can see the field velocity is inversely proportional it depends negatively on f. So basically, if you have a small f, you have a large field velocity, okay? And if you have a large field velocity, you're more likely to be moving with you're more likely to delay the onset of the oscillation. And that's why you have a larger relative abundance at the end. So that's why it depends negatively on f.
Mm-hmm.
Did I make myself clear?
Yeah, partially. Okay. Okay. Okay, let me think. And I have actually another question. So
Sure.
usually if we have this coupling, then the velocity, because of this axion field velocity, axion can release its energy density to gauge field production, dark photon production in this case.
Yes, yes.
Here you are doing opposite way. So
Yes,
there
yes.
is a dark photon background and it enhances the axion velocity, right?
Yes, good, good, good. So the point is that if you go to like much larger values of the E dot B, then the axion moves really fast, and then the axion starts to backreact in the sense that the axion itself starts to produce the dark photons really efficiently. But that happens at like even much larger values of the E dot B. The point is that if you're kind of around here, the E dot B background is making the axion move, but the moving axion itself doesn't produce that much photons.
I see.
Yeah. So the region where the effect that you mentioned becomes important is okay. I cannot be quantitative here, but it's somewhere up here.
Okay. Thank you.
But that's a very good question. Thanks. Okay.
So, Takeshi, I also have a question on this setup. So,
sure.
So you're assuming also, I guess, that in the dark sector you only have these dark photons. I mean, for you they're pretty much massless, no? I mean, it's okay if they're massless.
Yeah, the dark photons, yes.
The dark photons, exactly. But so that also means that you are assuming there is no other content in the dark sector, really. I mean, I'm saying if there are scalars or fermions also interacting dark scalars or dark fermions, then you can also, I mean, thermalize the dark sector in itself. And if you thermalize, then you end up with no E dot B, I guess, at some point, right? I mean, like in the standard model. I mean, if you have a thermal plasma, then you destroy the electric field pretty much, right?
Yes. That's
So,
a very good question.
Do you need to assume, I guess you need to assume also something like that there is no thermalization in the dark sector, so the E field survives until you need it, right?
That's actually this point one that I was about to talk about. Yes. No, but that's a good point. Yes.
Thank you.
Well, okay, I'll talk about this, and if you still have questions, let me know. Okay.
Great, great.
Good. So this slide is about comments for future work. Okay. So here, for simplicity, I talked about dark photons, and as I said, I was assuming that the dark photons. Let me see. Okay. Okay. The reason why I was considering dark photons is because if it's the standard model, E dot B, as Lorenzo said, the electric field basically shorts out after reheating when the universe thermalizes. And so the E dot B basically, even if they're produced in the early universe, they will disappear in a radiation-dominated universe. So that's why normally the E dot B of the standard model has a negligible effect on the coupled axion. But on the other hand, if the reheating temperature is sufficiently low, then the E dot B, even those in the standard model, they will survive, and this can impact the axion dynamics. Now going back to Lorenzo's question, so actually the story is similar, even if for the E dot B in the dark sector. If the dark sector is also, I mean, just having a E dot B in the dark sector doesn't mean that the dark sector is thermalized. But if the dark sector is also thermalized for some reason, then the dark electric field should also disappear. So in that case, you wouldn't have a dark E dot B. So did I answer your question, Lorenzo?
You did, yeah, thank you.
Okay, good. Thanks for the question. Okay, so those are the comments. Another point is that for simplicity, I assume the E dot B to be homogeneous. Instead, if the E dot B were inhomogeneous, what happens is that it would instead source axion isocurvature perturbations. This is also constrained strongly from CMB observations. So that's also something that would be fun to think about. And here I also basically consider the effect of E dot B's on the vacuum misalignment scenario, but this will also have an effect on the post-inflationary spontaneous symmetry radiant scenario. Basically, the E dot B background will affect the field dynamics, and it should also have an effect on domain wall formation So that's also something that should be fun to think about. But these I will leave for the future. Good. Okay. So I've been talking about two examples where the dark matter, I'm sorry, the axion evolution gets modified. But now in the final part, sorry, how much time do I have left?
You have, I would say, 10, 15 minutes.
Oh, okay. Good, good. Sorry, somehow
Yeah. Let's say 15. Yeah, easy.
Okay, good. Somehow when I do the full screen, I cannot see the time. But anyhow, thanks. Okay, so now I'm going to switch gears. And so far I've been discussing about axion dark matter maybe, but now in the final part, I'll mention that axions, they're also useful for explaining the origin of the density perturbation in our universe. So let me explain how this works. Okay, so the motivation here is the origin of the cosmic structures. So now it's pretty much established that the structures of our universe, like galaxies and galaxy clusters, they originate from primordial, like tiny density fluctuations in the early universe, namely the primordial density perturbations. And we also know from astrophysical observations that these primordial density perturbations were adiabatic in the sense that all the different components of the universe shared the same fluctuation, and it was red tilted in the sense that when you Fourier decompose the perturbation, the amplitude grows as you go to larger length scales, and also the density perturbation followed a nearly Gaussian distribution. So we know quite a lot about the primordial density perturbation, but what we don't know is where did they come from? Like where were those density perturbations generated by the inflaton or by something else? Okay. And of course, an axion-like field is also good at doing that. And here I will show that if you have an axion-like field coupled to a new confining sector, so this is something like the QCD, but not the standard model one. It's like a dark QCD group. If you have an axion-like field coupled to such group, then this can generate the density perturbation through the curvaton mechanism. So this will be the take-home message. And in order to explain how this works, I'll have to start by explaining what is a curvaton. So the curvaton mechanism is a mechanism for generating the density perturbation, not by the inflaton field, but by a spectator field called the curvaton. So the idea is the following. The curvaton is, as I said, it's basically a spectator field during inflation. So its energy density is very small initially. But after inflation, at some point, the inflaton decays into radiation, after which the energy density goes down like the scale factor to the -4. On the other hand, for the curvaton, at some point, it starts to oscillate about its potential minimum. And so then its energy density goes down like 1 over the volume, slightly slower than that of the remnants of the inflaton. So the point is that even though the curvaton density was initially much smaller than that of the inflaton, if you wait long enough, the curvaton will come to dominate the universe. And of course, at some point, the curvaton itself may also decay into radiation, but if this decay happens later, the curvaton will come to dominate the universe. And another point is that this curvaton is very light during inflation. I mean, that's the assumption. And therefore, the curvaton obtains superhorizon field fluctuations, which basically means that the energy density of the curvaton takes slightly different values among different patches of the universe. And as this curvaton comes to dominate the universe, or come close to dominating the universe, its density fluctuations gets converted into the density fluctuation of the entire universe. So this is how the curvaton generates the density perturbations of our universe. And hearing this, I think you already noticed that this mechanism is very similar to the vacuum misalignment scenario for axions. So I think you're already seeing that a curvaton would be a good curvaton candidate. This is even more the case when you think about the spectral index. So here I'm showing the power spectrum or the 2-point correlator of the primordial density perturbation, which can be parameterized as a simple power law of the comoving momentum. This power law is referred to as the spectral index. And you can compute the spectral index in the curvaton scenario, which turns out to be just a simple linear combination of these two terms. The first one is the curvature or the effective mass of the curve of time during inflation, and the second term is the time variation of the Hubble parameter during inflation. And on the other hand, from observations, we know that that the 2-point correlator is red tilted, which basically means that the spectral index is slightly negative at the order of 1%. So in order to reproduce this observed value, there's basically two options. The first is to require this time variation of the Hubble parameter to be negative at the order of 1%. This kind of requirement puts a pretty strong constraint on the inflation sector, and it basically requires that the inflation should be moving a super Planckian distance, and the model in particular has to be a 5-4 type inflation. So if you like this kind of model, that's completely a viable option. But if you don't like these kind of super Planckian excursion things, then the only remaining possibility is to require a negatively curved curvaton potential, namely a concave curvaton potential. But on the other hand, when you think about the axion, because the axion potential is by definition periodic, it naturally contains these negatively curved or concave regions. The thing is that if you randomly throw your axion along its energy potential, then roughly speaking, by 50% chance, your axion will end up on this negatively curved region, which can in principle produce the observed red tilted spectral index. So also from this point of view, the axion is actually a very good candidate for a curvaton. And to explain how it actually works, to make the discussion concrete, for this axion-like curvaton, I'm going to assume that this guy, this field, obtains a mass through coupling to a confining gauge group in the dark. So the point is that I'm going to assume that the axion coupled to some gauge group that gets confined at low temperatures. But it's not the standard model QCD. So the confining, the strong coupling scale is not that of the QCD, but something unknown. So there's basically two free parameters, which is the zero temperature axion mass and the decay constant, or the decay constant and the confinement scale. Okay, and so you have two unknowns, but fortunately you have two observations, which is the amplitude of the 2-point correlator and the spectral index, both of which can be computed in terms of the axion parameters like this. So at the end, you can uniquely fix your decay constant and the strong coupling scale in terms of the inflationary Hubble parameter. Okay, and also as a minimal model for simplicity, let's assume that the inflation decays instantaneously at the end of inflation, in which case you can compute the maximum temperature of the universe in terms of the Hubble parameter like this. And so you know the decay constant and the confining scale and the maximum temperature of the universe. And then you can find that there's a hierarchy between the inflation scale and the confining scale and the maximum temperature of the universe. So from the first inequality, what you find is that basically the inflation of Hubble is lower than the confinement scale. So it basically tells you that this gauge group is confined during inflation, and which is why therefore the axion actually feels a potential during inflation. And if the axion is in the concave region, this can produce this the red tilted spectral index. From this second equality, what this is basically telling us is that the cosmic temperature after inflation becomes larger than the confinement scale. And as a consequence, what used to be confined gauge group temporarily gets deconfined after inflation. And this temporal deconfinement plays an important role. So let me explain that. So the evolution of the cosmic temperature in this scenario is like this. So during inflation, the cosmic temperature is basically the de Sitter temperature, which is lower than the confinement scale. But after inflation, during reheating, the temperature becomes larger than the confinement scale, and then it cools down, and eventually it goes below the confinement scale again. And due to this temporal deconfinement, the energy density of the axion curvaton after inflation, it basically drops significantly. It does not go all the way to zero, because even though the potential disappears, there's still kinetic energy left. So that's why it doesn't go all the way to zero, but the kinetic energy also reaches rather quickly, so it goes down very fast. But at some point, the temperature becomes lower than the confinement scale. So the axion potential starts to emerge again. And so the axion energy starts to increase again. And then at some point, the axion starts to oscillate about its potential minimum. And then you have the usual story where the energy density goes down like 1 over the volume. And then it's the familiar story. Okay. So this is what happens due to the temporal deconfinement. And you may be thinking, what's a great deal? Well, this is actually a big deal, because if it were not for this temporal deconfinement, then the axion curvaton will rather quickly start to oscillate after the end of inflation. And then it becomes very difficult for the axion to dominate the universe unless you really fine-tune the axion matter couplings to be extremely tiny. And here, you should keep in mind that in order for this curvaton mechanism to work, the curvaton has to dominate, or at least it has to come close to dominating the universe. So the point is that due to this temporal deconfinement, it really helps. It delays the onset of the oscillation of the axion, basically because the mass disappears for a while. And this at the end helps the axion to come to dominate the universe and generate the density perturbation of the universe. And here I should mention that this temporal deconfinement is not something that I put in by hand. It's something that shows up as a consequence of trying to match with the observations. So the point is that all these things kind of work in the good direction to make the whole thing work. So here, as I said, the temporal deconfinement is playing an important role in delaying the onset of the axion oscillation. But I should also mention that there's one alternative way to delay the axion oscillation, which is basically to place the axion very close to the hilltop. So the idea is to basically make use of anharmonic effects in order to delay the onset of the axion oscillation. And this is a fine-tuned possibility, but I kind of like this about 10 years ago, and that's because this anharmonic axion curvaton, it also produces a rather large non-Gaussianity, which I thought was a nice prediction back then, but it soon got gorgeously ruled out, excluded by the Planck satellite results. So it's no longer valid. So now I think the way to go is to have a temporal deconfinement. Okay. Good. So what are the smoking guns? So the first thing is that, as I said, this axion curvaton produces nearly Gaussian density perturbation, but it also produces some amount of non-Gaussianity. In terms of FNL, it gives a positive and non-Gaussianity at order unity. This should be contrasted to single field inflation, which produces negligible FNL, and also to the vanilla curvaton, namely curvatons with a simple quadratic potential, which gives a negative FNL in the dominating limit. So this is quite different. The nice thing is that these kind of values for FNL is actually testable with upcoming large-scale structure surveys like spherics. So this axion curvaton is something that can actually be falsified or tested rather soon. So that's a nice thing. Another thing is that I said that the concave potential of the axion plays an important role in producing the red spectral index. But another important thing to keep in mind is that towards the end of inflation, the axion rolls towards its potential minimum, where the region where the axion potential is convex. So there, the spectral index turns to a blue tilt. So the thing is that you have a red tilt on large scales, and then you have a blue tilt on small scales. And as a consequence, you end up enhancing the density perturbations on small scales. And this can lead to the formation of fun astrophysical objects like ultra-compact mini-halos, which can lead to interesting astrophysical signals. And it's not just the two-point correlator that has a scale dependence, but the non-Gaussianity also runs. It runs from a positive FNL of order unity on large scales to a negative FNL on small scales. So this is also a fun prediction of this scenario. Okay, so this brings me to the last slide. So in the first part of my talk, I basically tried to point out that what is considered to be the standard lore of axion cosmology actually has a lot of wiggle room. And to show that, I presented two examples. The first was the inflexion mechanism. The idea was that when you have a kinetic mixing between the infiltron and the axion, this can lead to axion dark matter production even at very low inflation scales. And it also has the fine bonus that it can integrate the single field infiltron and the reheaton and the dark matter. It also opens up new axion windows. In the second part, in the second work, I showed the impact of primordial electromagnetic fields on the axion abundance. And in particular, the QCD axion can be completely excluded if you have a rather small amount of E.B in the dark sector. Okay. And in the last part, I showed that axions can also be a viable curvaton candidate, and it can generate the density perturbation of the universe. And it also has fun consequences observationally, like for non-Gaussianity and also its scale dependence. Okay, so that's quite it. Thank you very much.
Thanks a lot, Takeshi. I will clap. Questions? Also, perfect timing, by the way, yeah? Thank you. Okay, I see a question from Takahiro, please.
Could you go back to the figure of temporal deconfinement?
Sure.
I have a question about this. So there are several sections for this blue line.
Yes.
First, the kinetic energy is diluted by 8 to minus 6. And finally, coherence oscillation is 8 to minus 3rd. So what are other parts?
Okay, thanks for asking. So here, this drop is basically due to the quick disappearing of the axion potential. And it drops all the way until it hits the kinetic energy of this axion. And after which, as you said, the energy density of the axion is dominated by the kinetic energy, which goes down like 8 to the minus 6. But then, so this is what you're seeing. And then at some point, the temperature goes below the confinement scale, and so the axion potential starts to emerge again. And so that's what you're seeing here. But the point is that before the mass reaches the zero temperature mass, typically the axion begins to oscillate. So here is the region where the axion is already oscillating, but the mass is also growing. And so these kind of balance, and at the end, the energy density slightly increases. And then at around here, the axion mass asymptotes to its zero temperature mass. So after which the axion mass completely becomes time independent. And so the energy density just goes down like 8 to the minus 3. So that's why you're seeing this very complicated curve.
I see. And the energy is originated from the inflaton background, right? This increase of rho sigma.
Let me see. Basically, yes, in the sense that, so let me see, the potential is growing because it's kind of stealing energy from the radiation background. And
radiation background.
Yes, yeah. And the radiation background is sourced by the infilton. So in that sense, you can say that this is coming from the infilton.
Yes. Nice. Thank you.
I see Pablo, please go ahead.
Hi, I had a question about the inflaction, the first part of the talk about the kinetic mixing. Do you have considered the UV origin of such a kinetic mixing? Like if I consider the axion to be the phase of a complex field, then I typically get a periodic function multiplying that thing proportional to, say, the sign of the axion. That would affect your conclusions, right?
So you're saying that, okay, so let me see. I think your first question is the UV completion of this kinetic mixing. And I think you were also asking about that you can also have like couplings between the axion and normal matter, as long as the coupling has like a sign form. That's also allowed.
Well, I wasn't making the second question, although maybe it's interesting. I was thinking about a particular UV, like just saying the axion is a phase of a complex field, and how do I kinetically mix that complex field, and if I kinetically mix that complex field with the inflaton, then I just focus on the axion part, and that kinetic mixing part that you wrote, it also comes with a sine or cosine. Well, depends on the phase.
Okay, good. Yeah, so a nice one example which actually discusses like UV completion peacetime kinetic mixing is given by these works by these people in Bologna. And so they're interested in these like large volume string compactifications. And so they have in their scenarios, they have a lot of Axion-like particles, and one of them plays the role of the inflaton. And they also kind of like mix with each other. And basically their claim is that some correction to the Kähler potential or something at the end leads to a kinetic mixing between the axion that plays a role of the inflaton and the other one. But in their example, because this kinetic mix basically comes from like small corrections to the Kähler potential, the kinetic mixing tends to be small. But that's the example that I know. I would be happy to know if there's also other examples, but that's the one that I know. Okay.
You're talking about, I guess, Ciccoli and company.
Yes, exactly. Yeah. And
okay. Yeah.
And yeah, and I think, okay, since you raised, and this may not be exactly what you asked, but yes, the point is that other than the kinetic mixing, you can also have like usual potential mixing as in principle, as long as it doesn't violate the sign, the discrete shift symmetry, like sign of axion multiplying some random function of other fields. That's also a possibility. Those typically, I think, would tend to be higher dimensional. So I think their effect tends to be weaker. Of course, it depends on the amplitude of the kinetic mixing, but those tend to be weaker. But that's also a possibility. And I think we didn't investigate those too much, but I think you can also have something similar to our inflexion through those kind of matter couplings. I think those will be fun to investigate, but we haven't so far.
That sounds also interesting. Thank you.
Thanks for asking.
More questions? I do have a question, actually, possibly two. But so Takeshi, the first one on this slide that you're still showing. So at the end, also this axion has to decay, right, into radiation. So it comes to dominate the energy density. So you have a period of matter domination, and then it has to decay. So it means that you have to couple this axion to the visible sector. I mean, strongly enough. I mean, what's the bound here? I imagine it must decay into radiation before BBN at least, no? That's is that the constraint?
Right. Thanks for asking. I kind of skipped those discussions because I thought
because I'm wondering if you have these couplings, maybe they have to be strong enough. Do they affect everything else, or yeah? So
good. So for the simplest case, I consider the axion to be coupled to some gauge field. This could be photons or dark photons, whichever you prefer. And then, of course, as you say, you have constraints on this coupling alpha. The lower bound comes from the requirement that you want this to decay before BBN. On the other hand, if it's too large, it would decay before dominating the universe. So this is the upper bound. And you have two values because the actual constraints depend on the inflation scale. I didn't mention too much, but actually for this model, there's both lower bounds and the upper bounds for the inflation scale, which is 10 to the 11 and 10 to the 14. And depending on that, the lower bounds and the upper bounds for alpha also varies. But the point is that the upper bounds is not that strict, right?
Right, good.
But thanks for asking.
No, sure. And sorry, another quick question. You are assuming instantaneous reheating pretty much. If it is not instantaneous, does it change the picture or not much?
Yes, it changes the picture, roughly speaking, because you're adding one more parameter to the model. Yes, and yes, it does change, and it actually does change quite a lot. But I didn't think too much because it was a short paper, and I tried to keep things minimal, so I didn't investigate much. But yes, it does change things. At least qualitatively, it does. I'm sorry, quantitatively, it changes quite a lot, these bounds. Yes.
I see. Good. Yeah, I mean, indeed, also it's probably quite also, I mean, not so easy to study. I mean, possible, I guess, but yeah, sure. I mean, this is the first thing one wants to do. No, I agree. Yeah.
Mm-hmm.
Yeah. Thank you. More questions from the audience? I don't see more questions, so I want to thank Takeshi again. Thank you, Takeshi.
Thank you.
We clap again, I guess. And so, Sang-Hui, you tell me, should we reconvene, I don't know, in 5 minutes, 10 minutes? It's 10:07.
Maybe, yeah, we start 15. 10,
At 15, let's say.
10, 15,
okay, good.
5:15. Okay.
And Francesco is our next speaker. So again, we restart at 10:15. Okay, thank you, everybody.
7-minute break. So.
Yeah, 10:15 or 5:15 p.m. Korean time. Yeah, thank you, everybody. Speaker of today.
I'm sorry.
Not only now I can start. Okay, so we are resuming the workshop, and we have the second and last speaker of today and of the whole workshop, actually. So I'm very happy to have Francesco Schiavone, who is a student. Hello. He did this work at the University of Bari, I guess. And yeah, so he's gonna talk about axion-like particles from primordial black holes shining through the universe. So please, Francesco.
Hello, good morning, everybody, or good afternoon, depending on where you are. My name is Francesco. I recently graduated at the University of Bari, and thanks for the invitation and for organizing this workshop. Today, I'm going to talk about this paper here, which is based on my thesis work and which was written along with my supervisors. The topic of the paper is essentially the production of axion-like particles from primordial black holes and how this can be proved by observable signatures. So in the first part of the talk, I will introduce the concepts of axion-like particles, primordial black holes, and specifically Hawking radiations from primordial black holes. So how the spectra of axion-like particles from primordial black holes can be calculated. Then I will focus on the topic of axion photon conversions or ALP photon conversions, and how this can be how this process can be used to obtain some observable signatures, specifically astrophysical and cosmological signatures. Finally, I will briefly extend these concepts to the case of the decay into photons of massive axion-like particles. And finally, I will conclude. So the first part of the title, of course, is axion-like particles. And just a quick recap of axion-like particles in general, even though Takeshi before me already did a very nice one. So yeah, axion-like particles are essentially a class of particles which stem from the axion. The axion was first proposed as a solution to a problem in the QCD, which is the strong CP problem, and it was born as a Naumburg-Goldstone boson arising from the breaking of asymmetry, which is the so-called Peccei-Quinn symmetry. In later theories, which attempted to go beyond the standard model, there were several similar particles that emerged from the theories that shared that shared many features with the QCD axion, essentially the fact that they were pseudoscalar particles and that they were electrically neutral. So all these particles were called Axion-like particles, or ARP for short. And since then, there have been several production mechanisms for these particles have been studied both thermal and non-thermal, so that it is generally accepted that if axions or any axion-like particle exist, then a cosmic axion background should also be expected. So this that I'm going to talk about is just another way in which a cosmic axion background can be formed. The other part of the title is primordial black holes. Primordial black holes are supposed to be formed when density fluctuations in the early universe collapse below their Schwarzschild radius. And in recent times, they've been a very talked about topic because they've been invoked to explain several phenomena, including the origin of supermassive black holes, some gravitational wave data, and also the origin of dark matter. Now, primordial black holes have this property by which their mass at formation is related to the time they are formed. This is because essentially the mass is related to the form when portion of mass collapses below the horizon. So we have that there is a proportionality between the mass and the formation time, so that black holes formed later also are heavier. And an interesting fact is that primordial black holes behave as a matter component of the energy budget of the universe, so that the density between the black hole density and the radiation density grows as the scale factor in the Robertson-Walker metric. This means that it is possible that the black hole density becomes dominant and actually leads to a stage of early matter domination. In particular, if we impose that this epoch of domination lasts between the end of inflation and the start of Big Bang nucleosynthesis, we have that the mass of the black hole should be constrained within this range here. So in this plot, what we see is that while standard cosmology would imply a radiation-dominated epoch where the total energy density of the universe is essentially constituted, is essentially made up of radiation, followed by a matter domination epoch. In the presence of primordial black holes, we can have a radiation-dominated epoch followed by a black hole-dominated epoch, and then again a radiation-dominated epoch followed by the standard matter-dominated epoch. Of course, the black hole domination must come to an end, and as I said, we assume that this happens before Big Bang nucleosynthesis, and this happens essentially due to Hawking radiation. Now, Hawking radiation is essentially the property of black holes of emitting particles from their from their event horizons, thus reducing their own mass. In the case of an electrically neutral and non-spinning primordial black hole, the emission rate for Hawking radiation for particles of spin S is given by this formula here, which is essentially similar to a black body spectrum, except for these factors, gamma S, which are known as gray body factors, and that represent essentially distortions of the black body spectrum. And we will come back to this in a minute. The temperature of the black hole, so the temperature of the black body temperature in the sense of the black hole, is given by this formula here. So we see that lighter black holes are also hotter. And generally, we see that for the typical masses that we are interested in, the black hole temperatures are very high. A feature of Hawking radiation is that it is democratic, meaning that all particles are emitted as long as the rest masses are below the black hole temperature. So in this context, we assume that all the standard model particles are emitted plus one species of Axion-like particle. We want to stress that this is a non-thermal Axion ALP production mechanism, since the production of ALPs does not happen thermally by processes inside the cosmic medium, but they are emitted directly by the black holes. These gray body factors that I was mentioning earlier are generally quite complicated functions of both the particle energy and the black hole mass. And the form of the functions themselves depend on the spin of radiated particles. These functions are usually computed numerically, for example, via the Black Hawk program. However, we see that it can be shown that for very high particle energies, and so also for very high black hole temperature, the so-called geometrical optics approximation holds, meaning that all gray body factors tend to the same constant value. I mean, not constant, to the same asymptotic value given by this formula here. And this applies to our case, since, as we saw, the black hole temperature is much higher than all the particle masses in the standard model. Indeed, we can make a comparison between an Hawking spectrum calculating using the so-called geometrical optics approximation and the exact spectrum calculated using Black Hawk, and we see that the agreement between these two is acceptable in most cases. Now, another important property of primordial black holes and Hawking radiation is their lifetime. Now, to compute the lifetime of a black hole against Hawking radiation, what we do essentially is to calculate the mass loss rate. And this is done by integrating over the Hawking emission rate, integrating over the Hawking emission rate over the energy, and summing over all particle species. Now, this function here is usually written by sort of addition in this form with a function f of m, so a function of the mass of the black hole divided by m squared. In our case, we see that over the masses considered, this function is essentially constant, so we replace it by this numerical factor. And so we have this very simple equation to solve, this very simple differential equation to solve, whose result is this expression here, where we introduce the black hole lifetime by this formula. So we see that, of course, as expected, the more massive a black hole is, the more the longer it lives. Okay, so we see that we have two relevant timescales, I would say. One is the formation time, and we saw that lighter black holes are formed at earlier times. And the other is the black hole lifetime. So the time between formation and evaporation. And we see, of course, that heavier black holes also live longer. Okay. Now our task is to compute the spectra of Hawking radiated axion-like particles. And these are obtained essentially by integrating the Hawking emission rate over the black hole lifetime. This assuming an expanding and matter-dominated universe. So we assume that the evaporation essentially happens during the epoch of black hole domination. This leads to a shape factor of in the spectra, which has the form of a quite convoluted integral function. And for simplicity, we assume that the mass spectrum of primordial black holes is monochromatic, meaning that all primordial black holes are formed at the same time and thus have the same masses. Of course, there are more realistic assumptions that can be made depending on the formation mechanism. Sorry, on the formation mechanism of primordial black holes, and the various spectra are reviewed, for example, in this paper by Carr. And also, what we do is to calculate the spectra at the time of primordial black hole evaporation, and then simply redshifting them to the present epoch. This is an example of the kind of ALP spectra that we obtain. And a few comments on it are that these spectra are, the energies of these spectra are mainly in the 1 to 10 keV range. So they correspond to the frequencies of soft X-ray. They are independent of the initial black hole fraction. And also, these spectra have longer tails for higher black hole masses. In particular, for example, if we can compare the 10 to the 7th gram case to a thermal spectrum with the same temperature. And we see that compared to the thermal spectrum, the Hawking spectrum has a much longer high energy tail. A final comment is that on Hawking radiated ALPs is that if they are light enough, they will be ultra relativistic, and so they will contribute to X-ray radiation or dark radiation rather than dark matter. This contribution is measured as a deviation from the standard effective number of neutrinos in the standard model, which is a little more than 3, due to the fact that neutrino decoupling does not happen instantly. So the effective number amounts to a bit more than just the 3 neutrinos in the standard model. To compute this contribution, we can just use this formula where we employ both the ALP radiation and the CMB, and at the ALP density, sorry, and CMB density. What we found is a value of about 0.04 multiplied by this factor that depends on the number of entropic degrees of freedom at the time of black hole evaporation. Of course, this is an unknown number because we don't know how many degrees of freedom there will be beyond the standard model. So we just set this value to about 100 for convenience. We note just that in this case, the delta NF, our results for delta NF is compatible with the experimental uncertainty on NF as measured by the Planck experiment. Okay, so this was the basics of Hawking axion-like particles from Hawking radiation, but now we want, of course, to probe some signatures of this phenomenon, and we do that by using the ALP photon coupling. So we distinguish between two cases. We see that for very light axion-like particles, so below the nano electron volt threshold, the relevant phenomenon is that of ALP photon conversions, which, however, requires the existence of cosmological magnetic fields. And the upper bounds on these fields is currently of about 1 nanogauss. On the other hand, we have the case of heavy axion-like particles for which the conversions become negligible, and instead the ALP decay into photons becomes more effective. So we have these two processes, and both processes have the effect of producing high energy photons, which are injected into the universe, and which contribute to two phenomena, at least two phenomena, that are the presently observed cosmic X-ray background, or CXB, and also the process of cosmic reionization, which can be proved via the Thomson optical depth of the universe. Okay, so this is just a recapitulation of the current bounds on the ALP photon coupling constant. So we see that for most of the ALP mass range, these bounds are between 10 to the minus 12 and 10 to the minus 10 GeV to the minus 1. Of course, the situation changes significantly for heavier particles. Now, the basics of ALP photon mixing are encoded in this Lagrangian, which of course includes an ALP term, a photon term, and a mixing term or interaction term, which contains the ALP photon coupling constant. It can be famously shown that in the presence of a constant magnetic field, the Euler-Lagrange equations for this system can be linearized in this form, where we distinguish between photon polarization modes which are orthogonal and parallel to the external magnetic field. So we have several terms here. We have photon polarization terms, which depends on the 3 more terms that we will come back to in a second. Mixing terms, and also an ALP mass term. In particular, we note that the orthogonal photon mode does not participate in the mixing. So only the parallel photon mode mixes with the ALP field. And thus, in this case, the mixing problem is a 2x2 mixing problem. Now, these terms here, I've written them out here just to see what are the quantities that they depend upon. So we see that the ALP photon mixing term depends on the product between the ALP photon coupling constant and the transverse component of the magnetic field. The ALP mass term depends, of course, on the ALP mass and on the ALP energy. And then we have these 3 terms which contribute to photon polarization. We have a plasma term depending on the photon energy and on the free electron density. We have a term coming from the vacuum birefringence in QED, depending on the photon energy and on the transverse magnetic field. And we see that we have a different factor for the orthogonal and parallel modes, but we will neglect these additional factors in what follows. And finally, we have a CMB term, so a term due to the interaction of the photons with the background CMB field, which depends on the CMB temperature and on the photon energy. So just to recap a bit the significant quantities in our problem. Okay, so in the case of constant magnetic field, it is quite straightforward to see that the oscillation probability over a length x takes this form here, which very much resembles the oscillation probability for neutrinos. And I'm sorry, I keep okay. We have the mixing angle here, which is defined by this formula here, and also this oscillation wavelength, the oscillation wave number essentially, which is related to the oscillation length in this way. So we have a very nice and smooth oscillating probability. But in the case of a cosmic magnetic field or a primordial magnetic field, the situation is complicated by the fact that, of course, the magnetic field can't be homogeneous over all the universe. So we need to find some structure from these magnetic fields. And the simplest structure is a domain-like structure with a typical domain size at present of about 2 megaparsec and fields of about 1 nanogauss intensity with the direction randomly changing from one domain to the next. Of course, we also need to account for the expansion of the universe, so the fact that the size of domains stretches as the universe expands. And also the fact that the direction of magnetic field changes between domains makes it so that this is a full three-dimensional problem. So it is no longer a 2x2 mixing problem as before, but it's become a fully dimensional problem because, of course, there's not anymore a well-defined direction orthogonal and parallel to the magnetic field, because the magnetic field itself changes. Finally, we need to account for the fact that photons can also be absorbed by the intergalactic medium, and this absorption happens at a rate given by this formula here, where we have where we keep track of the photoelectric effect on hydrogen and helium atoms, and also Compton scattering on free electrons. Okay, so in practice, how do we account for all this? Basically, we build a sequence of redshift parameters, where the increment, or actually the decrement of each parameter corresponds to how much time the relativistic axion-like particles take to cross a domain whose size is, of course, related to the present size by the appropriate redshift factor. So I say that this is a decrement in redshift because there is a relation between time and redshift, so that a positive increment in time corresponds to a negative increment in redshift. And this is, of course, because more recent times correspond to lower redshifts. Okay, so by the relations that I previously showed, we can see how the various mixing parameters scale with the redshift parameter. So each the values of these parameters in the nth domains are related to the values of these parameters as present by these formulas here. And we also define this Q parameter, which is just the sum of the various parameters related to photon polarization. A couple of interesting facts is that first we see that the CMB term, so this green line here, dominates over all other terms for redshifts above 2000, so that conversions can be relevant only below this threshold. And also we see that the photon polarization term, so the Q term, this red line here, has a dip at some point. So there, this corresponds to points in time when the Q becomes 0, because we have the negative plasma terms that compensates for the positive QAD and CMB terms. So the fact that the photon polarization term becomes 0, and also the fact that we are assuming the ALP mass to be negligible, so there is no ALP mass term here, makes it so that there are resonant effects in the ALP photon mixing, because basically it's delta A gamma becomes the only non-zero term in the mixing matrix. Okay, so by following this paper by Evoli and others, we obtain this recursive formula for the conversion probability, which relates the conversion probability in a domain to the conversion probability in the previous domains. so we see that the behavior of this probability is much more complex than the simple oscillating pattern in the case of a constant magnetic field. And also that, as expected, there are resonant peaks corresponding to the points in time in which the Q term becomes 0. This formula, as we have already noted, accounts for the three main effects that we have discussed, which are the expansion of the universe, of course, the conversions between ALPs and photons, and also the absorption of photons due to this exponential factor here. Okay. Now, this was it about the ALP photon, the mechanics of ALP photon mixing. Now, let's see how this phenomenon can be exploited from an observational point of view. And the first impact we want to study is that on the cosmic X-ray background. So the cosmic X-ray background has been observed for several decades, and it is just a diffuse electromagnetic background radiation in the energy band ranging from about 0.1 to about 100 kilo-electron-volt. There have been several space experiments dedicated to this aim, such as the Charmed X-ray Observatory, and the result was that most of the sources of the CXB in the low energy part of the spectrum have been resolved, meaning that the spectrum in the low energy part has been attributed to point-like sources such as active galactic nuclei. But at higher energies, the picture is less complete, so we still don't know where a substantial part of the CXB comes from. This is just a plot recapitulating the CXB flux using data from several experiments. And it also features a power law fit, which is this black dashed line that we will come back to in a second. What we are interested in doing is to constrain the ALP photon mixing parameter. So what we do is to estimate the present X-ray flux due to conversions by multiplying the present ALP flux by the present conversion probability, which is of course obtained by evolving the recursive formula and, up to the present day. Now, the mixing parameter, so the product between the ALP photon coupling constant and the present day magnetic field, can be constrained if we impose that the X-ray flux that we obtain in this way does not exceed the observed one, and the observed flux is modeled by the flux that I was referring to, the fit, sorry, that I was referring to earlier, which is taken from this work here. And so we obtain a series of plots that look like this. And so basically we increase the ALP photon mixing parameter until these plots touch the lower part of the fit, so that And when we get there, we place the bound. We will come to this, we will come back to this to compare the bound that we obtained with the other bounds. Now, another small parenthesis that that we may discuss is how, in our scenario, the soft X-ray excess from galaxy clusters could also be explained. Now, there are several galaxy clusters which exhibit an excess luminosity in the soft X-ray spectrum. So we see from this plot that it is a plot of the ratio between the data and the cluster model. We see that at lower energies, the data and model badly disagree because, as I said, there is an excess luminosity at low energies. And it was already argued by Conlon and others that this could possibly be explained by some sort of a cosmic axion background, which converted into photons inside the cluster magnetic fields, whose typical strength is about of the order of the micro Gauss. In our work, we just show that by essentially following pretty much the same calculations as this work, that similar results can also be obtained if the cosmic axion background is a consequence of the evaporation of primordial black holes. Now, the other side of the story is the contribution of ALP photon conversions to the ionization history of the universe. Now, to briefly recap, the ionization history of the universe, we may say that begins at recombination, where the newly formed protons and electrons combine for the first time to form neutral atoms. It is then followed by an epoch known as the cosmic dark ages, where no visible light is present and most of the matter of the universe is neutral. But then at later times, there is a process known as the cosmic reionization, when the first stars and galaxies formed begin to reionize the matter in the universe, which is now essentially fully ionized. Okay, so we will see this in a plot later. But what is the role of ARPs in all of this? Essentially, ARPs may convert into high energy photons, and these photons may ionize neutral atoms which are formed after recombination. In order to estimate the number density of free electrons produced in the nth domain, we use this formula here, where we have the photon spectrum, the fraction of free photons, so the fraction of photons that are not absorbed in the nth domain, the fraction of ionizing photons, meaning the fraction that goes into ionization rather than other processes, and finally the number of hydrogen atoms that can be ionized by a single photon. So this formula is quite straightforward. And we estimate the contribution to the ionization fraction. So the ionization fraction is just the ratio between the free electron number density and the hydrogen, the neutral hydrogen number density. And its a standard value, which we denote with this zero superscript, can be computed numerically by codes such as the famous recfast code. Our contribution is, of course, at Zn is the sum over all previous, over the contributions of all previous domains. The general result is that we have this term, which enhances the ionization fraction with respect to the standard case. So we have this plot here of the ionization fraction. We see that before recombination, in the standard picture, we have the ionization fraction, which is 1 before recombination, then it drops as the recombination happens, and then it rises up at the reionization. The effect of light ALP conversions, so these 3 lines here, is to enhance the ionization fraction during the dark ages. We also have plotted the case of massive ALPs that we will come back to later. Okay, now the increased ionization contributes to the optical depth of the universe, which is calculated by this formula here, where sigma t is the Thomson scattering cross section. And again, what we do is imposing that the value of the optical depth that we obtain does not exceed the measured value by the Planck experiment. And we do so in order to constrain the ALP photon mixing. So we obtain plots that look like this, and essentially we place our bound when the calculating the optical depth exceeds the Planck value. Okay, so to recap, we have this exclusion plot where we place both our bounds from CXP and from reionization in a parameter space comprising the black hole mass M and the ALP photon mixing parameter, which is given again by the product of the ALP photon coupling constant and the magnetic field strength at present. We compare our bounds to the bounds from the CAST helioscope, the bounds from the observation of the supernova 1987A, and also the bounds from the CMB that that can be found in these 3 works. The fact that all these bounds are bounds on GA gamma alone. So in order to represent them on this plot, we have to multiply them by a magnetic field that we assume to be of the order of 1 nanogauss. So this is the case for the ALP photon conversions of very light ALPs. On the other hand, we have massive ALPs. And massive ALPs can decay to photon pairs with a decay rate given by this formula here. So it is evident that lighter ALPs have a very low decay rate, while heavy ALPs decay much more efficiently. Indeed, the decay is relevant only when the typical lifetime of ALPs is less than the age of the universe. This is accounting also for Lorentz boosts. So for the time dilation due to the relativistic motion of ALPs. So this brings us to focus on heavy ALPs. In this case, the only difference is that we obtain the photon spectrum by solving a Boltzmann equation, which includes photon absorption terms and photon production terms due to the ALP decay. But once we obtain the photon spectrum, of course, we can just the same evaluate the contributions to the cosmic X-ray background and to the reionization. So our bounds are represented in this plot, which is now in the ALP mass versus ALP photon coupling constant parameter space. And we only report bounds from reionization because we find that the CXB bounds are generally much weaker. Okay, so I've come to towards the end. So to conclude, what we may say is that the domination of primordial black holes is a possible occurrence in the early universe, and I mean, if these primordial black holes emitted Axion-like particles, there will be several observable signatures for this process. In particular, this would place very stringent constraints on the ALP photon mixing. It would be nice if this method could be extended to other particles, such as gravitons. Gravitons are emitted much more efficiently by spinning primordial black holes. And it would be an interesting case to study because graviton photon conversions proceed in much the same way as ALP photon conversions. However, the problem is that the graviton photon coupling constant is of the order of the inverse Planck mass, so about 10 to the minus 19 GeV to the minus 1. So this very small coupling constant makes it quite difficult to observe conversions. Just to conclude, I would like to point you to some interesting references. About primordial black holes and the Hawking radiation, we have a very nice review by Carr, which was one of the original proposers of the concept of primordial black holes along with Stephen Hawking. Then we have some papers by Dan Hooper and others, and also by Massino, Fanger and others about the production of dark matter and dark radiation from the Hawking evaporation of primordial black holes. We also have an interesting paper by Arbe et al. And others, sorry, which proposes an interesting precision calculation of dark radiation from the evaporation of primordial black holes. Recently, other works about Axion-like particles from primordial black holes have come out, specifically a couple of papers by Bernal and others, and this very, very recent paper, like a couple of days ago, paper by Calza and others. Okay, so I'm done. Thank you for your attention.
Thank you, Francesco. Thanks a lot. And thanks for being perfectly on time also. Nice. So, yeah, questions. I see Nayara is clapping. I didn't know if there was a question.
Thank you.
Okay, so I have actually a couple of questions. If so, meanwhile, I will ask. Let's see, somebody else also has questions. So one question is, I think you mentioned this already, right? I mean, in pretty much this work, when you take the magnetic field, right, into account, that's a primordial magnetic field, right, that you're pretty much considering.
Yeah.
And can you remind me what is the bound on that? Because so you're taking nanogauss, right?
Yeah, about nanogauss. This
right.
Was,
and what's the largest? Is there a bound on how large this primordial magnetic field can be? I mean, can you take it much larger than that in your calculations?
No. The nanogauss is the upper bound essentially.
It's already the upper bound. Yeah.
Yeah. There's a paper from the Planck collaboration where it is reported.
Okay. So, and I have another question also. Can you? I think maybe I missed it, but so how important it is that you have this population of primordial black holes that dominate the energy density? I mean, so the picture you described, you have these primordial black holes. They are radiating Alps, right?
Mm-hmm.
And then these Alps, they go through these photon conversions, or they decay into photons, and then you're looking for these signatures in X-rays, pretty much, right?
Mm-hmm.
And so why is it important that these black holes dominate the energy density of the universe early on?
Well, the general idea is that primordial black holes become dominant. So there is a moment in which there are like only black holes and almost no radiation. And then after they evaporate, they basically reheat the universe by emitting, by transforming into radiation and emitting all sorts of radiation, and then leading to the radiation-dominated phase. So this was the scenario that we worked in. Of course, yeah, there could be like a population of black holes which is non-dominant. Yeah,
and that would change your scenario. I mean, if they never dominate the energy density, then
that yeah, it would change because, like for example, this formula here.
Mm-hmm. Yeah, that wouldn't.
Which is a shape factor. This is calculated by assuming matter
dominated,
so,
right? Yeah.
Evaporation happened during the black hole domination. Of course, you could calculate this during radiation domination. You would have a different spectra, essentially.
Yeah, and it is, sorry, and also talking about the spectrum, can you go to the next slide, I guess, where you plot the spectrum of Alps produced, right, this one. So here I see in these mass ranges that you're looking at, right, we have pretty much Alps with the keV energy, right? If I, that's what I'm saying in this plot. So, I mean, does it, and at some point you also mentioned this mass to be 10 to the minus 9 EV, I guess, for the Alps, right?
Mm-hmm.
Does that matter? I mean, as long as the mass is quite below keV, these Alps are relativistic, no? And you're fine for a while. But you want them, I guess, to stay relativistic for a long time until the universe is redshifting. I mean,
yeah.
Right? That's the, I see. Yeah. Okay. Are there more questions?
I have one. So thanks for a comprehensive talk. So do you have any comment on the ARC detection between nano-electron volt and 1 electron volt that you didn't cover in this talk? From this
no, yeah, because it's a bit more fancy, the situation there, because
there are several studies on detecting this relativistic Alps in the usual haloscope experiments. So if this source is abundant enough, then maybe this is relevant for such studies. I just wonder whether you have any idea on.
Yeah, so direct, you mean like direct detection of Alps?
Direct detection.
Yeah, so we tried, we talked about this, but we found that the Alp flux by itself would be too weak to be significantly detected by helioscopes. So we didn't focus much on that.
I see. So it's hard to give a meaningful found from this source, from direct action.
Mhm.
Is it your, yeah, okay, temper or general conclusion?
Okay, let's see my last round of asking for questions. Okay, Javier, please go ahead.
Good morning. So I was just to conclude, I was thinking to ask the question. So what is the observation that is most likely to detect these Axion-like particles? Right. It looks like a study of reionization, like precision study of reionization. But I just wanted to know what is the expert's opinion, speaker's opinion.
Mhm. Well, yeah, I think that maybe also a study of like a precision observation of the CXB, if one could determine these specific spectral shapes, maybe that could be a signature. But of course, here we work in the approximation of all black holes having the same mass. So you would have to find an appropriate mass spectrum for the black holes and then compute the corresponding X-ray spectrum. Yeah, I mean, in the case of reionization, you have that, of course, the Thomson optical depth integrates over all history of reionization. So maybe, in a sense, it's you just get a number at the end. So maybe it's a bit less precise. But yeah, of course, you can study, you can do, as you said, a precision study of reionization. So studying reionization at different epochs and maybe find something interesting.
And would a 20 centimeter line study improve on the bounds? So would we have an impact on 21 centimeter?
Well, we didn't focus on that, but I can imagine it does, but I can't comment much more on that because we didn't consider that case.
Well, thank you very much.
Thank you.
Thank you. So let's see. Other questions? I don't see any more raised hands. Okay, if not, let me thank Francesco again. Thanks a lot, Francesco, for this nice talk.
Thank you for the invitation.
Thank you. And yeah, I think this is it then. Thank you, everybody, for participating.
Thanks, everyone.
Yeah.
Thanks a lot. Have a nice day.
Oh,
Oh, nice. So we have more participants than we thought, I guess.
very nice. Ciao, ciao.
Ciao, ciao.
Yeah, goodbye. Thank you.
Bye. Thank you, everybody.
Ciao. Have a nice day.